Okay, so this setup right here, we have a piston and this is containing water in it. This water is being pushed into this volume, and this volume is actually enveloped by a surface which is basically an interface between water and air, and these two plates are made of glass. The contact angle of water and glass, that's assumed to be 0. All right. And we are taking the system, so the thermodynamic system that we'll deal with, to be a thin layer of air around this surface, so above this surface actually, plus all of the water along with the surface inside of it. All right, and might as well actually take, this these plates in our system as well, right? Doesn't hurt. So you got these plates in our system, you got all of this water in our system, and there's an extra condition that the energy associated with the interaction between water and this surface, so the surface of the piston, uh, right, that interaction is basically the same interaction as interaction between water molecules, right? So it's as if this was a large pool of water and just had some water going inside, but this is a more controlled setup, whatever. The thing is, we are pushing this water very slowly, and we are having this pressure P, which is the pressure of the liquid, basically, because yeah, like the liquid's pressure is what it should be for very slow pushing, and this is the atmospheric pressure, right? There is surface tension, and that's why you have the atmospheric pressure being bigger than this pressure. We have to figure out what is the difference of the pressure. So what is P naught minus P? So one way, and of course let's just name some dimensions. So you got this whole length as capital R, and right, this is the radius of the plate. Actually, I should say this is not the radius of the plate, but the radius of yeah, this last circle you will have, right? So this radius basically makes sense. That's capital R, and then this circular arc, this will have radius small r. Okay, the contact angle must be 0, so this should actually be hemispherical, but then I couldn't draw it very correctly like that because yeah, but it's actually supposed to be hemispherical. Then this diameter, right, this is the diameter, and this thing is our radius small r. So we have to figure out what is delta P. One way to do this is using Young Laplace equation. So we can just say it's equal to gamma times 1 upon the signed R value, right, the first signed R value. So we just want P naught minus delta P, so the pressure is pushing outward. So for small r, right, small r, so let's just take one differential element over here. This is going like that, right? So these are our R, our radii basically, yes, and this tension is over here and whatever, right? This is pushing this being this is being pushed inside basically, right? Yeah, so that's why it's going to be positive. So you got positive 1 upon R, but then this other thing, so capital R, whatever that is, right? Yeah, these points, they are on this circular arc, and then okay, that force is being pushed in this direction. You get the idea, don't you? And because of that, it should be negative, right? Because it's in the opposite direction of what we usually have. So that's why I have negative 1 upon capital R, or something in the order of this thing. But it doesn't matter anyway, because this is actually much smaller compared to this. So it's approximately just gamma upon R, right? So that's one way of doing this. Now I will tell you the other way, which I like more, because it starts from very basic principles. Okay, so we are considering this to your system, right? This thin layer of air plus all of this water along with these two discs, right? Okay, the important thing to notice is that the entropy of this whole system does not change. I mean, I have explained that in the previous videos. So the entropy does not change. There's no heat transfer between surrounding and the system, right? The only thing is that the PV work is done on the system, right? There's no non-PV work because it's this air, right? This layer, I chose that specifically to not allow non-PV work, because if I just chose this film to be the last boundary of my surface, then there would be non-PV work, right? You would have bonds forming between surrounding molecules and these water molecules, and that's not what I want. So that's why I'm choosing this to be my system. All right. So since dq is equal to 0, our du is just equal to dw. All right, cool. And I mean, there's no non-PV work from these air things, right? But there is a thing, there is a bit of non-PV work. Well, okay, maybe we should not say it like that. Yeah, we should not. We shouldn't say it's work. We should say it's a part of du. Yeah, that will be better. Okay, so first of all, what is dw? Let's say that dv is the volume that changed. So this volume increased by dv, this volume decreased by dv. So the work done will be p times dv minus p naught dv. Just wait a second. Sorry, interruption. Well, does happen sometime. Anyway, p times dv minus p naught times dv. That's the work done, right? What is du? So first you got the surface energy change in this area. Yeah, so we'll just say that's gamma 1 dA1. All right, and there's also surface energy change in this area. And I might think, what is this thing? Why are we considering this area? Because there are interaction between water molecules and this surface, right? So we did say that this surface and water molecule have the interaction the same as it would be between two different water molecules, but this doesn't have those kind of interaction. It has a difference in the interaction, and that's why there is surface energy associated with that. Now, how much is the surface energy per unit area for this guy? Basically the surface tension. How do you figure that out? So to do that, just look at the contact angle. So for some contact angle like this, you got this liquid phase making contact angle theta with the glass plate or whatever this is, and then you got air over here, right? This is gamma 1, right? This has surface energy per unit area as gamma 1. This we'll just say is gamma 2, right? And the surface energy, right? Okay, this thing, that will be gamma 3. Oh, and by the way, I didn't say this, but this layer of air actually extends on this system completely, right? Not just this surface, but throughout the system, right? Okay, and also assume that the outside of this layer, so outside of this container, the interaction of that with air is the same thing as between two air molecules. So you can just neglect that interaction as well, right? And this only extends like that. Okay, makes sense? Cool. That's our system basically. So now we also have to consider the interaction between air and this disk. So that surface area is actually decreasing, and the surface area between water and this disk is increasing, right? So gamma 3 minus, this is like gamma 2 actually, gamma 3 minus gamma 2 times however much that surface area increase or decrease is, so dA2, right? This is the energy associated with that. Makes sense? But how do you even get this thing? So for this kind of configuration, you have a rule that basically says gamma 3 is equal to gamma 2 plus gamma 1 cosine theta. So as a mnemonic, you can think of force analysis, although that's a very bad way of thinking about it. There's obviously some energy changes associated with that, and then you are making them equal or something like that, right? It's not force analysis, but you can think of it like this to remember it better. Okay, what we are interested in is really just gamma 3 minus gamma 2, right? And that's just equal to gamma 1 cosine theta. Isn't that right? Oh, unfortunately it should be actually negative because dA2 is the positive quantity, right? Yeah. uh, right, gamma 3, that surface is decreasing, gamma 2 is, it should be gamma 2 minus gamma 3 in that case. Yeah, that's what I should have done. Whatever, magnitude wise it's still the same thing, right? Anyway, okay, we don't want that. Now we have this thing, and we know that theta is just 0 for glass and almost 0. So what do we get? We just get equal to gamma 1. This is just equal to negative gamma 1 dA2, right? And uh, dW is this thing, well, it's just equal to negative delta P times dV, isn't that right? Okay, so now our equation is basically gamma 1 dA1 minus gamma 1 dA2. That is equal to negative delta P times dV. Alright, and now let's just approximate some stuff. So what is dA2, right? You got pi r square as this area, right? It's just going to be basically 2 pi r dr, capital R, of course. So this thing, it's negative gamma 1, and you got 2 pi capital R dr. And what about this guy? So dA1, right? So that's the area of this complete thing. Now that area is approximately 2r times 2 pi r. I know, you might think, well, maybe this is not the area, it's different, it's not scaled up. But yeah, you might think all that stuff, but actually do the integration and you'll see that this is actually a good approximation, because it's like the integration of 2 pi x, where this is just that distance, like that's x, and then times th, right? But then x is very close to capital R, because small r is 0. I mean, okay, small r is almost 0 in comparison to capital R. Does that make sense? Right. Then this is just going to be 2 pi capital R, and then integration of dh is just 2r. Make sense? Okay. So now we figured out what a1 should be, right? Yeah, okay. So what's dA1? It will, I mean, dA1 with respect to capital R, not small r. Yeah, that is going to be equal to 4 pi small r, right? So that's just negative, okay, it's not negative, it's positive, gamma 1 times 4 pi small r, and then dr, right? That's supposed to be there, the differential of this guy, right? Should be capital R, sorry. Right, that's there, and this is actually equal to negative delta P times dV. So what is dV? Once again, we are going to do a bit of approximation. Volume of this whole thing is approximately pi r square, pi capital R square, right? And that times this height, so this times 2r. Yeah, so the derivative of this thing with respect to capital R, that's just going to be 4 pi r times r, right? Just put that in there, 4 pi capital R small r dr. That's necessary, that differential is supposed to be there. So this cancels, that 4 pi cancels as well. Okay, yeah, just 4 pi cancels, we don't care about it. Hey, you know what, no, let's not cancel it. Hey, I think we messed up somewhere. It's not supposed to be just yeah, it's not supposed to be just negative gamma 1 dA2. It's supposed to be, actually negative 2 gamma 1 dA2, because there are two such surfaces, right? Exactly. So this is going to be 2 times the factor, and that's why the first term is actually 2 times of what it previously was. So it's this thing, and now 4 pi will cancel out. So you just got, negative gamma 1 and then capital R plus gamma 1 small r is equal to negative delta P times capital R small r, right? So that just means send that over there, delta P capital R small r, that's just equal to gamma 1 times capital R minus small r. And then instead of writing gamma 1, I'll just write gamma, because yeah, that is the surface tension that we have to deal with, right? The surface tension between, or okay, surface energy per unit area between air and water, right? Okay, so dividing by this thing, just get 1 upon this minus 1 upon that. Makes sense, right? Oh, it should be the reverse order, right? 1 upon small r minus 1 upon capital R. So even energetically, you can see that delta P is indeed just gamma times 1 upon small r minus 1 upon capital R. Well, there we go. Wasn't that nice? Yeah, really. So even though the force seemed like it's actually going in this direction and not, yeah, but the thing is, it really is like this. That is how it is. So to a good approximation, right, we just can write this as gamma upon small r. That should do it. And it is already an approximation. I mean, we did all of this to get this thing. But yeah, if you approximate even further, you can write it like that. That's all I had to say. See you guys in the next video.